Every year, we lose 18 million people to cardiovascular diseases. 95% of the people die before reaching the hospital. From every 10 cases, 9 do not survive the cardiac arrest, while the last one is left with severe conditions. This is what happens when a cardiac arrest patient arrives.
Code blue, ground floor, Eaton Building, admitting department.
The goal in emergency is always to stabilize the patient and then to move them where they need to be.
And so I knew that I had to act quickly.
Seconds count, and minutes make the difference between living and dying.
I just looked at her and I said, "Stay with me. Stay with me."
If this is how serious it is in hospital, imagine what happens outside of the hospital. Saving time is not a luxury, it is a necessity. In case of emergency, the location is sent to the drone immediately, which will fly directly to the emergency scene, providing the AED device. Making a drone was not simple. That is why it is important to be organized and follow a cohesive plan to attain the required outcomes, all from scratch. Our plan is divided into 3 main stages: getting accurate readings from the sensors using Kalman filter, controlling the motors using PID controller, and finding the shortest path using 3D motion planning. After successfully implementing the drone, comes the testing part. To make it easier, we designed a simple user interface which consists of 9 options, which I'm going to explain briefly. The first option calibrates the drone to our range of signals, and here is an example of how the user interface interacts with the drone. Once the mode is chosen, the interface is going to walk the user through the process. First, it will apply 100% of the force to the motor, which should produce a beep sound. Then we apply 0%, which should produce another beep sound. Then a third beep sound as a confirmation of a successful calibration. The second option is done when the motors are already calibrated and ready to run. The third option provides direct access to the motor speeds, and this is useful to find the hover power of the motors. The fourth option runs the drone at the coded hover speed. This is useful to find if there is a mismatch between the coded weights and the actual weights. The fifth and the sixth options are both used to access the PID controller directly. This is useful to test the different kinds of scenarios that the drone might be subjected to and observe its reaction. The seventh option is used to get an inside look of the system flags, motor speeds, target location and orientation, and whether the sensors are working correctly or not. The eighth option runs the whole system and shows the important information that is needed during the testing process.
Despite the complicated view, it's actually quite simple. As we can see, all the motors have almost the same value, which is the hover power required by the motors. Later on, we will see how these numbers are going to change according to certain situations. First, let's see if the sensors work properly. As a test case, we are going to tilt the drone in its pitch angle. What we should see is an angle reading that expresses the actual tilt of the drone. As we can see, the pitch reading is almost 45. Let's try rotating the drone around a different axis. That looks promising. However, did that resonate in the PID controller? Let's rewind back a little bit. As we can see, the motors on the left are pushing harder, trying to return the drone back to its target position. However, in this case, the motors on the diagonal are the ones that are pushing harder as they are trying to rotate the drone back to its location.
Path planning is a computational problem to find a sequence of valid trajectory points in the space. So we had to make sure that the drone is capable of flying autonomously and arrive on time. So we had to plan the path. Our main goal is to introduce a fast, reliable drone that can take the AED to the patient as fast as possible. Search algorithms are used to find the path from start to the goal. We use satellite imagery to get an image from a satellite at the required location. There are many search algorithms that finds this path, as a fast computationally efficient search will not affect the overall time as the fastest path. A-star algorithm is similar to Dijkstra's algorithm, but it uses a concept known as heuristics, which means it makes an educated guess. So instead of having to check every possible route, it skips checking some of the possibilities and makes the algorithm faster and get the shortest path. After the algorithm is done, the Raspberry Pi provides the controller with the path trajectory points.
After guaranteeing fast arrival of the drone, we worked on making the trap safe by avoiding any obstacles. So we decided to work on a deep learning model that will help the drone to detect any nearby object and avoid it. Our first trial is implementing the object detection model on a Raspberry Pi, and we indeed managed to do that by using TensorFlow Lite. But after implementing it, we faced a huge problem, which is the low processed FPS, which reached 2 FPS. We were implementing this solution on a Raspberry Pi 3, so we managed to get Raspberry Pi 4, but unfortunately the results didn't get much better as it reached 4 FPS only. We searched for the problem and found that we can use USB Coral accelerator, but due to COVID-19 we couldn't get it, so we have to find another solution. Our second approach is implementing object detection using a web server. So we implemented the server using Node.js, but after knowing the fact that Node.js uses a single thread to handle incoming connections, we have found that Node.js wouldn't help us. So we decided to use Flask as it's lightweight and will get the task done. Consequently, we used HTTP requests and responses to send frames from the Raspberry Pi to the web server. But after testing this approach, we unfortunately found that the results got even worse as FPS became less than 1. After some research, we found that the problem was in the protocol used to connect between the Raspberry Pi and the web server. Therefore, we have to use WebSocket to connect between the Raspberry Pi and the web server. And fortunately, the FPS reaches 21 frames per second. And we managed to send frames to the server and get the feedback from the server, so we have successfully implemented live a reliable object detection model that sends the feedback to the drone in real time.